static piping. So that's the piping in between this tank and the pump. So it could be, the tank's halfway up the wall, the pipe out of the tank is, 10 feet to the floor, there's an elbow, and then it goes into that pump. That's static, it doesn't change, we need to calculate it. Big thing that we do on that is we pick up energy because we're 10 feet. We have an additional 10 feet of energy that we have, but then we have to subtract the known friction losses for that fluid to go through that pipe. So once we got that, we know what our suction is. So we have typically in a flooded, we have known energy that will allow the flow to go through the pump and come out to the other side, okay? So we have that calculation. Then we go to our discharge. We walk the pipe. How far is this going? How much of it is horizontal? What size is the pipe? How many valves? How many elbows? Is it vertically going up in the air? So on and so forth. And where we dispensing? What tank? What place where we're actually dispensing? Is that tank that we're going into pressurized? All this. So then we take that. We figure out what his flow requirement is. He wants 50. So based on 50, we calculate the friction losses, the vertical rise in pipe, and put a figure together on that to give us our total discharge head. And we take the two together, whatever those known numbers, subtract the difference of the known energy versus the energy that's required, and that's where we come up with our total system head. So you have suction, discharge, and then total system.
And what would you use the total system head for? Just
Size in the pump.
Size in the pump.
Yep. The other is suction lift. So we're pulling up, which two things. It requires me to get a self-priming pump, and how we do that with centrifugal pumps is they make this gooseneck casing or elongated casing that allows fluid to retain in the casing. So this casing would be much bigger. There would be a pocket of fluid that retains in the casing, and it recircs. So what they're trying to do is be able to create vacuum. By having that fluid recirculating in there, we're able to create the vacuum needed to pull the fluid into the pump. I think I might have. Description of the self-priming pump. So here's basically the self-priming pump, the elongated casing. So what they're doing is they're retaining that fluid. So this fluid would be recirculating into the pump and basically creating that vacuum, that the seal needed to produce vacuum inside that casing. And it recirculates until it fully pulls up to the fluid. When the pump stops and doesn't operate, the chamber is still filled with fluid. So that's how we compensate on being able to self-prime or pull fluid in. So going back to.
So Dave, if your supply is below your pump, will you always need a self-priming pump?
Yeah, absolutely. Now, there's other arrangements that you could use. Here's one. So basically that's this pump, vertical, with a long shaft that actually goes into the sump. Okay. Very typical in sump applications. So the casing and the majority of the components of this pump would actually be submersed into that sump.
Okay.
Number one issues with this is do-rags. All the rags, if you will sweep it into the sump, you always, I can't tell you how many I've seen needing to be repaired, and that's the number one thing. 10 rags shoved into the pump. So the only difference between the flooded and the suction lift is this static piping and lift assumes a negative value in your overall system. So in the case with the flooded suction, we had no energies we could subtract. In this case, there is no subtraction on the suction side. What your static, what your discharge requirement is you got no additional energy supporting that, the discharge off your suction. I could send you this. It kind of breaks down exactly what we just went over here. Let's see what else. I didn't know what how far we get into this. One of the other things that I should bring up is the word ANSI. So in the pump world, people talk about an ANSI centrifugal pump. Well, what does that mean? It's, you know, this is the American National Standards Institute, okay? So many products go through it as you want a level of a standard that everyone meets. Why? So that way pumps are interchangeable. It helps the industry because now you're not, each competitor can sell to a standard, so that way pumps are easily replaced and people can reap the benefits and be able to sell more. So what ANSI is, all that is it's this center line design. So you got two pumps. You got an end suction, and you got then an ANSI, and the next one is API, American Petroleum Institute. And what they're doing is the standard is saying, hey, we want the pump center lined. So we want this discharge in line with the suction, like so. It dictates the flange connection, 150 or 300 pound flanges. It dictates the thickness and the overall size of the casing. So that's basically it. When you hear ANSI, that's what they're talking about. It's not something overly complicated. It's a standard in which the casing sizes are made.
So if you have a Gould's ANSI pump, you could take that out and put in another manufacturer ANSI pump, that same size, it'll bolt right in.
Correct. So the other thing about ANSI is, since that's how it, so one thing that about ANSI, you know, I'll talk about other aspects because there's been a lot of changes that's going on. So you're stuck on sizes. You'll see that people will use the terminologies. I got a Gould's 326 or a 1516 or a 216 or a 2156 or whatnot. So when they talk about that, what that means is they're giving you the suction, your discharge, and impeller. So they'll all fall within line. If it's an ANSI pump, this is your range. Your smallest pump is 1.5 by 1 by 6. 1 inch suction, 1.5 inch suction, 1 inch discharge, and 6 inch impeller. Why do you think the suction is bigger than the discharge?
Doesn't cavitate.
Yeah, excellent, yeah. We don't want it to cavitate, so you always see that. There's occasions with some pumps that the suction and the discharge size is the same, but not in the case with ANSI. ANSI pumps, so the majority is centrifugal pumps. You don't want to have the possibility of cavitating. So all of these use basically. So when you get up to multiple sizes. I don't have the breakdown, but you have the same bearing frame. So basically, from these three sizes, one bearing frame, but these sizes here use the same bearing frame. These sizes use the same bearing frame, and then further along. But they all dictate the same thing. So this is your standard sizes. You've got 1.5, 1/6. To a 3 by 2 by 6, 1.5, 1/8, all the way to a 4 by 3 by 8, and then 2 by 1 with a 10-inch impeller, to a 4 by 3, and so on. So this is the standard across. The majority of all manufacturers in the business typically go up by a 6 by 4 by 13 pump, and then when you get into some of your larger manufacturers will handle the larger size pump, the 8x6, 10x8. Now, mind you, when you start getting up to this size of pump, so your 8, your 10, a lot of times now they reduce the speed on you as well, so.
Now with the ANSI spec, the impeller will not be trimmed.
Yes, it will.
Oh,
Yeah,
it will be.
Yeah, so it's just telling
That's
you.
just what
the
the
max size.
manufacturer. Okay.
Yeah, so that's,
Dimensionally on the outside of the pump.
yeah, yeah. So, and then API, I don't have the breakdown on that, but it's the same thing. It's, API usually has, like, instead of having feet here, they have side-mounted feet. Some of the reasons for that is temperature, if it's supported on the side. You have, expansion due to the temperature. It's better suited to expand on a side mount, and they have other specific standards, but that's, just so you know what you'll see. But oil or gas, you know, petroleum refineries, if you guys aren't in there, you're probably not gonna come across too many API pumps. ANSI is definitely typical. Now, what the industry is doing is called sub-ANSI. And what sub-ANSI is dimensionally, so where your flange connections are, it meets that qualification. Okay, so you can go into the place, and but they do a smaller casing, okay, or a different size casing. So if you're an ANSI guy, you're like, well, you could go with a thin casing, it might not be too good, which potentially could be the case in some aspects and some manufacturers. Or what a sub-ANSI allows you to do, if I'm building my casing a little bit differently, I can get better efficiencies. I can change that and allow my hydrodynamic design to be better, more efficient. So you see a lot of that. They want to be able to go into the ANSI location, but they'll change and modify what that overall casing dimension is. And then you have an end suction, and the end suction is basically you got your suction side, but your discharge side could either be on the right side, it could be on the left side, it could be somewhere else. So you run into that as well, and basically you're not meeting any standard as a typical end suction pump. Here is a couple things. Here's a multi-stage pump. I did bring this up. So one of the things is that in a centrifugal pump I can generate a lot more pressure, but it means that I get a much bigger impeller, and I keep making that impeller as big as I can. I can generate a lot of pressure. Downside is I need this big motor, and I'm putting out a lot of flow. So they had to figure out a challenge of how do I produce more pressure without going through all this. And one of the ways they do it is using multiple stage. A stage is all, when you hear the word stage, all that means is an impeller. It means there's more than one impeller. And some of these pumps have up to 15 impellers stacked one on top of the other. And all they're doing is each time the fluid goes through each impeller, you're increasing your velocity and then increasing your ability to generate pressure. These pumps, depending on how many stages you put into it, I think the most is about 1,000 feet you can put out of these. A lot of times, because they get big in size, they go onto this vertical mounting position. If you look here, you were asking this. This is actually, some of these motors do have a pressure sensor and a VFD already mounted on that motor. This is a typical design that's used in like reverse osmosis, Rhodey type systems, booster systems, and like you know, if you have a skyscraper and you're on the 20th floor and you would like some water pressure, you know, this is what's used. They usually take these pumps and there'll be, you know, a line of maybe 5 or 10 of them connected together, and as the demand and pressure increases, another pump comes on, and is able to maintain that pressure. And that's what that's used. Again, the manufacturers recognize, well, I can sell more if I provide that pressure sensor, and you know, you're able to put a pressure, a booster system together with integrated instrumentation.
Okay, on that pump there, like on the suction side,
Mm-hmm.
it basically comes in, goes up through all those impellers, and then comes down that tube to the discharge.
Mm-hmm.
It's just building, get higher pressure, boom, boom. Every time you go to an impeller, it builds off that, builds off that. It's just like another pump there, building pressure.
Almost like what we saw with the peripheral, although in the peripheral we were using vortexes, right, to transfer energy through a vortex. But almost, you know, it's almost similar. We're creating more centrifugal force every time it goes through an impeller. For a little self-priming. And here's your test. You guys would want that.
You give it to him later then, why don't they get through the whole thing?
Yeah, we give it to them
So before and then after, and then we'll grade Dave.
Hopefully you guys took some notes, right?
on the test.
Yeah?
Don't worry, we'll give it to Dan.
There you go.
A customer had a application, he's trying to build pressure like up to 2,000 PSI, and he has used a Moino screw pump.
Yep.
I mean, you couldn't do something like that with those centrifugal stages, right?
No, that's up there. That gets into a positive displacement pumps, which we'll hit on now. And I have, speaking of a screw pump, I have a whole pump here, so we'll take a look at that one later as well.
Shouldn't talk about Dan like that.
So let's get into the next pump out there. So you have centrifugal, and then you have what's called positive displacement pumps. And we're going to be reviewing. There's several types of positive displacement, but we're going to be reviewing, at least on this presentation and the next, rotary type of positive displacement pumps. Positive displacement, where they're different than a centrifugal, they use what I guess a fixed displacement of fluid. Okay, so in the case with the rotating, every time that shaft rotates 160 degree, I have a known fixed flow. Okay? So based on 10 RPMs, I could get so much flow, and if I increase it by 1,000 RPMs, I progressively increase on that flow. There's other factors that we will go into, but basically, essentially, that it is. So I'm taking the other thing is they use all the same principle, is that I take a cavity, I create a cavity on the suction side of the pump, and I collapse that cavity on the discharge of a pump to produce flow. The other part is reciprocating pumps. That could be a piston pump, where I'm reciprocating, right? And I'm pulling back, drawing fluid into a cavity, and I'm pushing that fluid out to produce flow again. So you get a reciprocating, and that could be, in your case, that double diaphragm pump is a flux. It uses a flexible diaphragm, but it's a reciprocating type positive displacement pump. Okay? There's single diaphragm. There's a ton, but the two breakdowns on a positive displacement is rotary and reciprocating. Okay? So the technologies, and we'll go with most of them. $30 billion pump market. 80% of all pumps are centrifugal. The remaining is positive displacement. You can see 6% of that is gear pumps, 4% of that is a reciprocating type, aggressive cavity or PC pump, which would be a Moino, is 3%, peristaltic or hose tubing pumps would be two, lobe, and then there's a lot of other types of different technologies would make up the remainder. So our focus on this one is the rotary gear. So most widely used PC pump on the marketplace. It comes into two common designs. One is an internal gear, and the other is an external gear. The first one we'll go through is the internal gear design. So it's got two working parts, your rotor and shaft and idler gear. So how this pump works is this is your driven gear. And what you're seeing here, it's actually the outside piece of this pump. And this is your idler gear. Basically, it's statically mounted. It rotates, but it's rotated by the driven gear. So it's just in there. Your drive gear is actually what's turning your idler gear. It's just, I guess, shaft or pinned in place. And then what we have is a crescent right here that allows us to create cavities. So basically, your flow in this pump comes in, and we open up this cavity here, allow fluid to come in, bring it through, and then we cut the cavity out. And as this rotates, both sides have fluid that come up to the discharge of the pump. And I think I get an example in the next slide here. And then here you can see the flow. So we come in, we fill out these cavities, okay? So we're opening the cavity on our suction side, comes through, we're retaining the fluid, because the one thing on your rotary is slip. What causes problems in this pump or reduces our flow or our ability to create pressure is if we have slippage in these cavities, okay? And that could be running too slow, could create slip. Running too fast could create slip. If we get a thick fluid and we're not allowing that cavity to fill all the way, could be a problem. So, but anyways, on the design things, fluid comes in, gets brought into the cavities here, separated by our crescent, and then out on the discharge of this pump. The nice thing about this design is some of these pumps do up to 2 million centipoise thick glue, adhesive, and they can even do some light. One of the big things was liquid asphalt. A lot of liquid asphalt used for these pumps, so that they are pretty versatile. So one of the downfalls is it has a cantilever load, and we didn't talk about that. So does centrifugal pumps, and I'll get into what that means. How you see this assembly is you see how it's elongated, and you got a bearing on the back end. So basically, we cantilevered over. Okay. So one of the issues you have is deflection. So deflection of fluid will actually bend that shaft, create vibration, and increase wear. But we have that same inherent issue with centrifugal pumps as well. That's why getting as close to the BE point is desired. Also, making sure that our NPSH requirement is being met is needed, but it is important. So as we get away from that best efficiency point, basically the best efficiency point means that all the fluid is hitting this eye and the pedal and it's operating effectively. If we get deflection, we stop moving away from that eye. As we move away from that eye, we create stress and deflection, increase our vibrations and whatnot. So some pumps cantilevered, others have straddle mount. When we talked about that mag drive, we had bushings on both sides, closer to the impeller and on the back side. That's known as a straddle mount design, and you reduce your deflection wear by going to that. So the next one is your external gear. How this pump operates, and actually this should have, this one should have, it should have been animated. But how this works is the fluid comes actually into the pump through your suction side, and is picked up with these two gears. One gear is your driven gear, and the other is your idler, just like the other pump, and I could show you there. But the fluid's picked up, and the cavities are created by these two gears. So fluid's not going through the middle of this pump. It's getting picked up in these cavities. These two gears are rotating this way. So we're picking up the fluid on both sides, bringing it around this housing, and out to produce your flow. Nice thing about these pumps is varying viscosities. We have pumps the size of your pen, all the way up. Speed ranges are substantial on these.
Can they
Actually-
shear the product?
Yes. Yeah. So if you have, yeah, if you have a low shear product, this would not be the pump to use. So your polymers or in the pharmaceutical hand creams or acne cream or gels that have low shear property, you want to stay away from that. So here's actually a pump. This is actual pump. Just I'll pass this around. Just be there is a magnet attached to this, so any electronics, I don't want you to mess it up. But see this bottom gear right here is attached to the magnet. The magnet. This is a sailless pump, so the outer drive magnet, which would be attached to the motor, would come over on this, and as it rotates, it turns the pump. This is idler, it's just pinned in place, and is driven by that drive, the drive gear. This is a straddle-mounted design. I have wear rings that are in the housing, and I have sleeves or bushings tied into both the front housing and the rear that slide onto that shaft. The gear materials are, this would be a PTFE, a stainless steel gear. I can get them in all different materials. Metal on metal requires a higher viscosity product. And plastic, I will have limitations. If it's all plastic, I have limitations on pressure. If I have high temperature applications, I can get these gears trimmed. Because they're so close together, if I go into a high application without trimming those, it will gall because you have that thermal expansion of the metal. So I can pass this around. You guys can freely take this thing apart. Again, I just electronics in the metals. Drop it there. Stuck to the mag. You can see up here as it goes around all your major components. I'm gonna say, and if you look at that, so we get this housing piece. Yeah, this actually is slightly different than that. But we get this housing piece, and one of the issues with the gear pump is that housing, after years of use, wears out. And basically, you're left replacing that whole housing. Well, they finally caught up and said, well, what if we do a replaceable liner? That way you don't have to replace the housing. So nowadays, some of the, and I'll go into some of the advantages, but I'm not sure if I specifically point that out, but they'll have a replaceable inner liner rather than you replacing that whole housing. But as I was saying, one of the nice things with this design is we're supported on both sides. That gear is actually in the middle, so we don't have any deflection to worry about in this setup.
So those gears need to be lubricated as well with the liquid, right?
Yeah, the gears, I wouldn't Yeah, you're not gonna be able to run any of these pumps dry. But you don't really need lubrication for the gears. We use the process fluid to lubricate the bushings and the wear plates.
So what can't you pump with this type of pump?
Well, on this pump, again, we're not looking, you're definitely not gonna be pumping any solids with this pump. Clean fluids. We prefer some viscosity, although we can do a full range. But oils, a little bit higher viscosity is good with these pumps. It's actually desired. So oils, glues, solvents. We do a lot of like chemistry, caustics, and those are the big. Sitherm is a big thing if you have heating and cooling. Again, we can get up to with that magnet design about 475 degrees F on some of those heating. So like a Sitherm or a Daltherms would be a great application for those.
Lower volume flow for that?
Yeah, so on the max on like this pump is typically around 50 gallons per minute, and you're able to do about 200 PSI. So again, the other thing is a positive displacement pumps are inherently self-priming. They will prime, so you don't have that issue like a centrifugal pump. And here's so like I was telling you, some of the advancements that they're making in the industry is, years ago we had about 46 parts, and they're knocking it down, they're reducing the size, value engineering. If they can reduce parts, reduce their cost, increase performance, and making it easier for the customer to repair, then they hit a home run. So that's what they're trying to do. Some of the changes is like the on this pump, instead of just having those bushings, they actually make them into a block. So instead of having two sleeves, now you got one, right? One component. And it knocks them out. Here's the liner that I was talking about. So here's your housing, just like on the other one. But this liner would then be pressed in to reduce the wear on the housings. Your gears are fixed in place to hold the drive gear and the idler gear. And they even gone to the extent of putting all the nuts into one assembly. But that's the move on to the industry, and that's how we're improving. The other piece would be not so much with the gear, but overall in general, it's instrumentation integration movement. So let's talk about some of the components. So there's two basic gear types. There's a spur gear, and you can tell spur gear because the gears are straight. That's probably the more basic and more common design out there. The other is a helical. Helical gear is on an accent or on a helix angle. So they're just off tilt a little bit. Basically, they're able to handle more capacity. And they also run quieter. If you have a light fluid with these gear pumps, they are sometimes noisy. You can hear them screaming away. Not ridiculously loud, but you can hear them. But as you increase the viscosity of fluid, you get a much more quieter, happier pump. So there's a couple things in a gear pump that determine the displacement. And displacement's key. So basically, one known is your speed. So whatever your speed is, you're going to have a fixed displacement based off of your rotation. But that's determined by the size of your gear, how long, how wide your gear is, to figure out what your actual gear displacement is. And you can see here, so we take our gear displacement times it by your motor speed, and at no pressure, we get our, what's called our open flow rate. So in this case, they're saying, hey, I get a known fixed displacement at a 0.5 milliliter per revolution, times that by 2,000 RPMs of the motor, and I can put out 100 milliliters or 1 liter per minute out of that pump. There's sailing points, and this is the most important aspect of a gear pump. Your main sailing points, you can see A is where your teeth and housing connect. Your second is in the middle of where your teeth between gear and gear meet. And then C is the two sides, and you see the carbon wear plate in the design. So you want to be able to sail off all those areas. So you can see here, the fluid comes in, goes into each of these points, and we have slip points here. That where if these sail points are not in close tolerance, we create slip. Now naturally on a gear pump, if we go too slow in speed, our slip increases. So there's a limitation, even though I can tell you that on 1 revolution I get a 0.5 milliliter, right? But I might have a high rate of slip, especially if I have higher pressure on the discharge side. So there isn't reason, I'm not gonna operate too many pumps at 10 RPMs. There's issues with that. And even when you go into the curves or data that are published on a gear pump, they always select an RPM range. So you're never gonna get, the displacement on 1 rev. They'll probably give it to you in 100. Here's our fixed displacement at 100 revolutions or 10. That way it's more in line than if you went and calculated, divided by 100 and said, hey, I get this per 1 rev. It might not be in line. And the reason for that is slip. So that's the important aspect. Now, why that liner I brought up? Obviously, we're using that housing. If that comes out of tolerance, there's issues. So having a replaceable liner is an important thing. Now, what happens when the gear wears? So when the gears wear or the lining starts wearing, we have two things that happen: reduced flow rate and reduced pressure. So, but we can compensate by that by increasing speed. So, one of the things that I've been looking at is we talked about VFDs and pinpointing, dictating to the customer through a VFD when it's time to change out gears, because we could start an application at 30 hertz, running half speed, and say, hey, by the time you get to 45 hertz on that speed, it's probably time for you to replace the internal components. Because we can adjust for that wear, and then you'll get to a point where it's not practical anymore. But you do have that level adjustment on the pumps. The other thing that, and I'm not sure if I get a slide, but a couple of manufacturers have what's called a, what's the name of it? A cavity, I don't remember the word. They got basically what they do is they have a cavity that they create that rides on the gear. So basically what that does is it mimics the housing.
Is it a shoe?
Yeah, so what it does is basically it is your internal housing, and it has an outer spring on it. So that way, as your lining wears or gears wear, it pushes out to keep that tolerancy for a longer period of time. So it compensates for the wear. The name's skipping me.
Micro pump action.
Again here, this shows, you know, exactly, so the flow in this slide is going this way. We're pushing the flow out, and again, your main slip areas is your front, your rear, in between, and at the teeth. So if we're gonna get slip in the pump design, that's where you're gonna see your wear. Just like your centrifugal pump, these designs are offered in 3 different sealing types. So we have our packing, which we went over, our mechanical seals, and then main selections of carbon, silicon carbide, and even tungsten is our typical materials, and then sealless, mag driven as well. And here's a good slide that kind of shows you how the mag drive works. So we have our 2 gears. This is our drive gear right here. This is our housing, a static O-ring in this setup. So your drive gear is connected directly to a magnet. Your idle gear is sitting in place being driven by your driven gear. So your inner gear, this is a containment housing that's coming around. This is your motor shaft. On your motor shaft is a magnet. And again, so this magnet's turning and rotating your inner magnet. In the case with the magnets, depending on the manufacturer, it could be it's usually could either have a stainless steel liner and jacket, or it could have like PTFE, carbon reinforced PTFE, or other encapsulated material. Again, you want to be particular on what material this magnet is, because that's actually in your process fluid. Okay? Curves of a gear pump are a lot different than a centrifugal pump. You can see that very linear. There's no real curve to it. And the other thing is these curves are based on speed, speed and pressure.
Hey, what's linear?
What?
Linear on a curve, that just means it's the same.
Straighter, yeah,
straighter.
I mean, the centrifugal curve was a curve. These are straight lines, and you can see even where you have the higher viscosity, even straighter. So what we have here is the same thing. Actually, it's a little bit, this is even a little bit different. So you got your pressures here, your capacity here, which on the other one was in reverse, I believe. And then each of these are, and I don't know how well you can see, but each of these curves are based on speed. So in this case, the majority of these pumps operate between 1750 RPMs. But we have an interesting line, micro pump. Some of those gear pumps go up to 6,000 RPMs. So there is, they are able to go up there. But the majority of what's out in the market, especially in the industrial sector, would be around 1750 RPM. So 750 RPMs up here to 300, and then I figure out my pressure, I do my gallons per hour, and then this is my horsepower. Okay, so just a little bit different than that. And then the change here is, and you'll see this typically on these pumps, there's multiple curves, and the curves are based on viscosity. So this is 1 centipoise. Typically you would have 10 centipoise, 100, 1,000, 1,500. It's about several that you're able to get on this pump. So we'll go through an application. Now we got 2 gallons per minute at 60 feet, and we're basically doing the same thing. So I'm going to be, or 60 psi. So I'm going to need roughly a 3/4 horsepower at 1450 RPMs. two things with this, is if I reduce speed, one, the important aspect of positive displacement and why they're unique and I think fantastic for metering applications is because I'm operating on a fixed displacement, I can vary speed all day long and I'll still be able to produce 100 PSI. I can't do that with a centrifugal pump, right? I lose my flow and I lose my head pressure. On this, I can do whatever. I can go through a lot big speed ranges, and he's still going to be able to get enough pressure in his system to meet that. So it's fantastic for metering applications. Two, so if you get somebody interested in a gear pump and you're not selling a VFD or talking to them about a VFD, you're missing an opportunity. Should be. It should be a package deal. It makes the most sense for that operator to be able to have a level of controllability with this equipment. So yeah, on these applications, we go from all over the place. Heating, cooling loops, oils, lubricants. You guys work with job shops and machine shops. You know, those pumps, that cooling, that recirculating, water application, boiler applications, laboratory equipment, all over the spectrum. In municipal, we got pumps that non-metallic that are metering chemistry, bleach, and sulfuric acids and other things. So as far as application-wise, we're very diverse and all over the spectrum of all industries with this type of pump. Other than sanitary, they're not cleanable, so you won't see them too much doing the food process. So again, some of the basic questions, flows and pressures, your temperature, specific gravity, viscosity, is it abrasive? Says they're not, this pump's not the best at handling abrasives. Crystallization, that's a big one, is, is crystal's gonna form into that bushing, you saw the sleeve bushings, stuff gonna gunk that up and allow it to wear out premature. Does it have lubricating properties? Is this a continuous or intimate? What type of drive? And always the description of what the piping arrangement should be. Clear advantages. We don't have that overhung load. I talked to you that we do have a broad speed range, even though the majority are operating at 1750. The other big thing is no pulsating flow. When you get into a reciprocating positive displacement pump, you've got a pulse in that flow rate. So that means difficulty with like a flow meter downstream, and other ways to detect what your flow is. Water hammer concerns and some other things that come with pulsating flow rate. The range of materials, like we discussed, pretty broad range. Handles entrained gas. You got known liquids like bleach being the big one that actually off gases. And what happens is for other pumps it could be a potential issue or causing it to need to reprime itself or whatnot. These pumps will handle that slug of entrained gas and just keep on moving. The flow meter downstream won't like it, but the pump doesn't mind. You can get it in the sealess design. Handles a broad range of viscosities, very small in overall size, and it's bi-directional. The downside is you gotta have clean fluids. You got a linear flow rate loss. As I was saying, we compensate that with increased speed. But as you increase speed, you increase your wear. So it's high shear rate, which you had brought up. It requires 4 bearings and bushings. And lastly, it can damage if dry run. Again, some of the advancements that are out there is people now have bushings and bearings that have some level of dry run capability. But just a rule of thumb, don't dry run the pump, never a good thing. Applications, liquid asphalts, chemical dosing, oils, fuels, lubrications, syrups, corn syrups, molasses, resins, coatings, adhesive. As far as price, they're relatively inexpensive in the world of positive displacement pumps, and they handle a wide range of applications. Any questions on the gear pump?
There you go.
So
There was an internal and an external, sorry.
What?
Yeah,
I didn't understand the difference.
okay. Alright. This is,
Yeah.
alright, so that's the externals. The external rides on the outside of the gear, okay? So
Okay.
it rides on the outside of the gears, okay? So,
Pulls it from the
comes
cavity and
around,
from-
both of these are turning, the fluid is coming around outside, on the, inside wall of the housing.
Okay.
So as this pump's turning, the fluid's coming in here, and it's getting picked up in this cavity by these teeth. And these teeth are driving the fluid this way, right, opposing each other. So it's riding externally on the outside of the gear,
Gotcha.
okay?
I was thinking the gears were
That's what I was thinking.
inside or outside of
Yeah.
the unit. I mean, how's that work?
Flow.
Yeah.
That's where it splits the halfway thing.
Yeah. So on this one, we're splitting, we're actually going internal between the two gears. Your drive gear on the outside, with your inner crescent and your idler. So as that drive gear rotates, the fluid's actually going in between both of the gears.
Okay.
So the big difference is you have a degree of separation, right? Because your idler gear is meshed at your discharge point more so than on your discharge, on your I guess, before your suction and right after your discharge point, you're meshed together. But on your suction side, we have a higher cavity or a larger space, which makes the big difference between the two, the internal and the external. This one is able to do higher viscosity fluids. So you're looking at millions of centipoise of handling versus, I would say, maybe 15,000 centipoise for the internal.
What's that unit you
External.
keep referring to? Centiploid?
Yeah, centipoise, that's
I'm not familiar with that.
the density of the fluid, thickness, how thick it is.
Okay.
So
Somebody
water
gives
is
you
X and.
Yeah, it's a wa-
Viscosity,
Pressure is in pounds.
Okay.
Yeah, it's,
Viscosities in centipoise.
yeah, so like water is 1 centipoise,
Okay.
and ketchup would be, 5,000 centipoise.
Peanut butter would
Be 50,000
Gotcha.
or 100,000.
Will an internal always do the 90-degree discharge versus the external always doing the straight through discharge?
Yeah, typically, yes, yeah.
Cool. Thanks.
So for you guys out there, are you more in, I'm sure your product mix or your customer mix is diverse, right? But what do you guys see more down in your territories? Is it more food, more manufacturing, industrial, pharmaceutical? Does it just vary?
It varies a lot.
Yeah.
Depending on the territory, I know where John is, I know there's a lot of food down your way, right? You know,
We buy far sell and service more centrifugals than we do gear pumps. But that's because we don't go after the gear pumps, because That's a little more scary than centrifugals.
Oh,
Because you can really screw up a gear pump.
Now, I noticed you had triclover, so little plaque, so do you guys handle the triclover pumps
Yeah,
too?
the alpha valve, yeah.
Yeah.
What were we, that metering application is what I'm going back to, and you said, well, it's good for metering, but not for food.
Yeah, so when you get into the food, cleaning, cleanability, if you see the design, right, how am I cleaning that?
Right.
It's not knocked downable. Now, there was a company, Niagara Pump, years ago, I think they're now out of business, that actually designed a clean-in-place gear pump, and it was made for like a sausage manufacturer or something like that. And they tried to put it out there, and it didn't take off.
Alpha valve has those.
Yeah.
They're CIP-able gear pumps.
Yeah, so maybe that's where Niagara, maybe they sold off to Alpha Laval. But years ago they came out, but you typically don't see it. They're not relatively they don't lend themselves easily to clean.
There's a couple of standards on there. It's clean in place, or they have it's an E-hedge, which is a European standard for cleanability too. So.
Yep.
Yeah.
And when you get into like, well, you guys are Alpha Laval, you get into a low pump or a centrifugal pump where you can knock it right down, clean it up. They just don't lend themselves for that.
Well, I think when he was talking about metering, he was talking about you know what your displacement is gonna be.
Yeah.
Based on the revolutions, right? So if you wanna pump 2 gallons a minute, it's easy to set that up with the speed to pump 2 gallons a minute consistently.
Right.
Okay, whereas with centrifugal, you're not gonna get that consistent flow,
Okay.
right? So I think that's what Dave meant by metering. Is
Yeah,
that-
yeah, exactly. And I was thinking of the application you went in with me, where we wanted to meter a certain amount in each
Yeah.
container.
Yeah, it was some sauce we were trying to meter into a container that they had some chicken in there, I don't know what was going through it,
Yeah, right.
but, and then they were gonna vacuum pack it, but,
So what kind of pump were we presenting to them then? Recall?
I forget actually which
Yeah.
one we were metering there. We weren't doing, I don't think we were gonna do it with timing, I think is what we're gonna do it with the sensor
With
eye
that
that was
eye,
on there.
right, that's right,
And
that's
we're
right.
just
That
gonna
was
time
hit
it, as far as what type of pump it was,
We were pulling more out of
see,
it too, yeah.
Yeah, but I think it was more with the sensor, if it runs for a second or 2 seconds, you're gonna get so much displacement that
Right.
it was gonna turn off and on with that.
With
sensor.
that.
Right.
Okay.
You're almost inherently going to be move into a positive placement on metering applications.
Yeah.
Batching, you can do batching with a centrifugal. You take the centrifugal pump and do a flow meter. It dictates how much flow went on to shut off the pump. But if you're going to do a metering or dispense like that, you're almost always pushed into a positive displacement.
Yeah.
Because you have a better level of controllability on that, what actually goes on. Years ago, and we'll go into the screw or the progressive cavity pump in a second here, but like I had to do a dielectric grease application, and basically I had to put a very small flow into wire, squirt in the wire, and I went out and I got the positive displacement progressive cavity pump, which we'll see, and put it to a servo motor to be able to control exactly where that shaft is on 130 degrees. I was able to inject that with a high rate of precision. Well, that's almost like your application with the gravy. It might be like would be a good like a reciprocating pump. Two things to look at it. I could reciprocate multiple times to produce your fixed flow rate, or I have pumps that would do one stroke
Right.
is your full dispense of gravy done. So there's a lot of different ways.
Yeah.
One thing to keep in mind, centrifugal and positive displacement. Centrifugal, you can shut off a valve and it's gonna sit there and slip. Positive displacement, it's positive displacement. If you shut off a valve, either it's gonna stall the motor out, or it's gonna break something. Chances are it's probably gonna break something. You're gonna break a line or blow a line apart, because there's no, unless it has a relief valve on it, but
Yeah.
there's no slippage inside there.
Yeah, and I'm kinda shocked I didn't put this in here, but yeah, that's, one of the most important things is, yeah, multiple things will happen. If you shut off a valve and the pump is on, if you're lucky, you blow your pipeline, or you know, or if you're lucky, maybe it's the pump, depending what it is, but you are either gonna blow your pipeline, damage the pump, or both, or damage both of them. Cause you're continually putting a slug of fluid, and a slug of fluid, and a slug of fluid. It's not stopping until. Now, the nice thing with the air-operated diaphragm pump, because you're driving that pump with air, okay, at a known pressure, so that pump's being driven at 75 PSI, it's a 1-to-1 ratio pump. So if you close a valve, once you equal 75 PSI on your discharge, the pump stops. And then you open the valve and the pump starts going again. So that's one of the nice things with the air-operated pumps.
I think we're going with a peristaltic pump for that application, like a master flex or something. I think
Nah, we wouldn't have done that, I couldn't say that word.
Yes, you could.
We're getting close to lunch. Do we wanna take a, do you want me to keep going? Cause
The
I'm on
pizza
my
should
next
be
one.
here in probably another 10 minutes or so. Go ahead and go and we'll stop for lunch. Yeah. Are you getting into a long session or is it a,
I'm getting into, progressive cavity here. I get the pump.
you think we should stop then before we?
Yeah,
Okay, let's stop. Yeah,
You
let's
want-
stop.
You
Then
can
we'll-
bring it out, I guess, and show somebody, right?
Just bring it out.
We can hold up stuff for lunch. The pizza should be here soon, so.
Okay.
Don't let me